Now we're going to start talking about different geologic environments and what types of rocks are formed where. So observe some familiar environments and think about what types of materials are common here. Okay, let's not worry too much about writing and filling in the notes right now. Just observe what these different environments are, and then we'll come back to filling in this little table in your notes. All right. So glaciers. We're finding these up high in the mountains where things are nice and cold. Glaciers carry all sizes and shapes of material, including large boulders. And often glaciers will move like a big frozen river of ice. So again, the material they're associated with, they can carry all different sizes, but they are such huge things moving along. They crush whatever they're moving over, and so it ends up creating sort of a powdered material along with it, as well as dropping great big boulders and rocks of all different sizes. The material associated with rivers. Rivers carry silt, which is real teeny tiny. If you have it in between your fingers and you rub your fingers together, you won't feel any grit. That's how fine silt is. So rivers carry silt, sand, and cobbles. Okay, cobbles are about the size of your hand. Okay, so silt, sand, and cobbles. Our next environment is lakes, and lakes are usually associated with silt and mud. So very fine-grained sediment settling out because the water's not moving very fast. Okay, steep mountain fronts are going to have large angular rocks. So if you think about the very first image we looked at today, and the very steep mountain front, that's where you found the landslide. So when you have a landslide occurring, the rocks are not sorting themselves out based on size. It's just a huge heap of rocks breaking apart and falling downhill. So you're going to find all different sizes and lots of angular rocks. Sand dunes. You'll never guess what they're made of. Sand! So sand dunes are nearly all sand, and they're really cool actually. If you ever go up to a sand dune and gather some of the sand and either roll it between your fingers or take a look at it with a little hand lens or a little magnifying glass, you'll see the sand is actually perfectly spherical. They're these perfect little spheres of quartz, and that's because they've been weathered, they've been eroded, broken down for so long that they've rolled out into these perfect little spheres. They're really neat. And that is specific to wind-blown sand. Alright, beaches. Many beaches are mostly sand, but some have rounded stones as well. And then we also have the offshore environment. The sediments there include mud and the remains of sea organisms, so things like broken down coral reefs, clams, dead fish, all kinds of stuff, any kind of shell or marine organism can often be incorporated in offshore sediment. So it's a great place to find fossils in old offshore deposits. So all of these different environments and the type of material that's found there, they're all formed in normal surface environments, meaning they don't have any extraordinary heat or pressure going on. This is just what the surface of the earth does. Rocks move from a high elevation downhill to a river or a lake and work their way down to sea level. That's a normal surface environment. So these are all sedimentary rocks. Sedimentary rocks. So this is our first rock family, sedimentary. It's made up of sediments or pieces of other rocks. So pieces of sand, little pebbles, pieces of shell, pieces of clay, and so on. Alright, now we can get back to our little chart in your notes. So rock families formed in hot or deep conditions, the term for those, if the rock is formed from magma, it is igneous. If it is changed by heat and pressure, it is metamorphic. If it is formed from precipitation from hot water, it's called hydrothermal. Okay, so take a minute. In our 4 families of rocks, and it doesn't matter what order it's in, but as far as order of presentation here, the first ones we saw were sedimentary rocks. So number 1, sedimentary rocks. And explain how they form. They form in normal surface environments from pieces of other rocks, from sediments. So number 1, sedimentary rocks form in normal surface environments from pieces of other rocks or sediments. Number 2, igneous rocks. They are rocks formed from magma. Okay, so even if it is ash erupting out of a volcano, that ash is originating from the magma. So rocks formed from magma are igneous. The root of that, the IGN, you can think of it as ignite. Okay, it's hot, it's melted, and then it re-solidifies. Okay, so rocks formed from magma. To be an igneous rock, it has to have melted completely. Number 3, metamorphic rocks, changed by heat and pressure. Metamorphic rocks are changed by heat and pressure. So the difference there between metamorphic and igneous, even though metamorphic includes extreme heat, the rocks never melt completely. Okay, they never melt into magma, because once they're magma, they're an igneous rock. They're no longer metamorphic. So it's just enough heat to alter them, to change them, but not enough to melt them. So metamorphic is changed by heat and pressure. And then number 4, hydrothermal is the family of rocks. And they're generated from precipitation from hot water. And precipitation in geology is not referring to a rainfall or snow or anything like that. It's referring to precipitation of minerals. So minerals that were dissolved in this hot water come out of solution and are deposited. You can think of it kind of like if you have very salty water and you let the water evaporate, the salt is going to form crystals on the bottom, so you would say the salt precipitated out. Okay, so hopefully you've got this all written down on your little table, and that has consolidated your knowledge about the 4 families of rocks, including sedimentary. Basically, sedimentary is made of pieces of rock. Igneous is made from melted rock. Metamorphic is made from high heat and pressure without melting. And hydrothermal is precipitation from hot water. So what can happen to a rock? If we start out at the surface, okay, we've got a rock up on the surface. And maybe in this mountain range it breaks off and it makes its way down into the river. So that is erosion and transport. So weathering, at the start of it, weathering can mechanically break apart a rock or can chemically alter a rock exposed to sunlight, rain, wind, plants, and animals weathering produces loose material or sediment. So this is how we get the sediments for our sedimentary rocks in the first place, is weathering. Okay, erosion. Erosion strips away loosened pieces of rock and transports it via gravity, glaciers, flowing water, or wind. Okay, so the erosion is taking those little bits that have been broken apart and moving them somewhere else. Okay, transporting them downstream, working their way from a higher elevation to a lower elevation. All right, and once they decide to stop, where they can't be transported any further, deposition occurs when sediment comes to a rest. So we're going to be having a sedimentary deposit here at the mouth of the river, where these sediments settle out and are deposited. So once deposited, sediment can be buried and compacted, and this leads to a process called lithification. Just like lithosphere, the root of that was rocky, lithification is turning into rock. Okay, taking a pile of sand and compacting it and cementing it together so that it forms a sandstone. That process is lithification, and that's how it becomes a sedimentary rock after burial. So sedimentary rocks can be uplifted after burial without anything else happening to them at depth except lithification. So at this point of burial, we can bring it right up to the surface, or we can have this next step, which is deformation and metamorphism. Buried rocks can be heated, deformed, and converted into a new kind of rock. This is metamorphism. So we're applying heat, we're applying pressure, and we're metamorphosing that sedimentary rock. Now it is a metamorphic rock. Okay, so at this point, we can either uplift it up to the surface as a metamorphic rock and the process starts all over, or we continue to add heat and pressure. Okay, if we continue to add heat, we're going to melt that rock completely. So now we've got magma. Rocks exposed to high temperatures can melt, and melted rock can cool and solidify at depth or by rising to the surface as magma. Once it reaches the surface, magma is called lava, so it can be erupted as lava. Or if it cools at depth, it can be uplifted up to the surface as a solid rock already. At any point, buried rocks can be brought back to the surface where they're exposed to weathering, and the whole process starts all over again. Okay, so really it's not as circular as it seems to be, because at any point you can take a sedimentary rock and bury it and turn it into either of these other types of rock, either metamorphic or igneous rock, where we've melted and solidified it. Or we can take a metamorphic rock and uplift it to weather it. We can take a metamorphic rock and add more heat to melt it down completely, and so on. Our next slide is taking a look at some different rock deposits from different environments. So if we compare this rock on the top left to deposits from two environments at the bottom, which environment has deposits most similar to the rock? Okay, so the first thing you want to do is take a look at the questions being posed in your notes. What distinct features are visible in the top photo? Okay, what do you notice about pieces of rock that are included there? What is their shape? What are their various sizes? Are they all the same size, all the same shape? Okay, then I would apply that same question to the images below. Is the bottom left all the same shape? Are they the same variation in sizes? What about the image on the bottom right? Are they the same shape and the same range of sizes? Alright, so I'm going to tell you the image on the bottom left is a deposit from a steep mountain front. And if you think about what we talked about just a moment ago with the sedimentary rocks and what you find at a steep mountain front, you find angular rocks. Okay, all different sizes. So this would be resulting from a landslide where everything just came down. There was no time for these edges to be worn off. Okay, as opposed to the image on the bottom right, this is from a river with pebbles. So you've got varying sizes, but the shape of them is all the same. They're all smooth, they're all rounded. Okay, and so the river with pebbles is more similar to the image in the upper left-hand corner because the cobbles, the pebbles, all the bits that it's made out of are all smooth. Okay, so what distinct features are visible in the top photo? What I notice is you have very small sediment, you have medium-sized sediment, and you have large sediment. So a range of sizes, and they're all rounded. They're all kind of spherical. Okay, there's no sharp edges. And which environment produces similar features? It's going to be the river with pebbles. Because in the river you've got little bits of sand, you've got little pebbles, and the water rushing over, that's all going to be rounding out, sort of sanding the hard angles off of all of these rocks. Alright, there are a few rules that geologists use to figure out the relative age of rocks. So these are all principles of relative dating. And I'm not talking about dating your cousin. What I mean here is how do we figure out how old the top layer is relative to the layer that's just below it. Okay, so that's what we mean by relative dating. So the first principle we use is the principle of superposition, and that is what is demonstrated here in this image. So on the left, in a sequence of layers, the top layers were deposited last, so they're the youngest. So in this case, this outer sort of reddish layer is our youngest. On the right, the sandstone was deposited on top of older metamorphic rocks that were exposed at the surface. The sandstone, therefore, is younger. So another way to think of this is each week you're printing out your notes for this class. So at the beginning of the semester, if you start making a pile of them and you set down your notes from last week's lecture, and after we're done with this one, you'll put another, this stack of notes on top of it, and so on and so on and so on. And by the time it's the midterm, oops, you forgot to look at your notes all semester. Where are you going to look in that stack of papers to find your notes from the earliest lecture? So your oldest notes, where are they going to be located? Anytime you're talking about sequential deposition, so putting things down over time, the oldest is always going to be on the bottom. Okay, so you're going to look for the oldest material at the bottom, the youngest, the most recent material at the top. That's the principle of superposition. Seems pretty straightforward, right? Okay, that's our easiest one, and it gets a little more complicated as we go, and then at the end we're going to put them all together, and then it's really fun. Alright, the next one, the next principle, is the principle of cross-cutting relationships. So, the younger feature can cross-cut older rocks or features. So on the left here we have a fault that cuts across or cross-cuts layers. It is younger than the layers. Right? So those layers had to be there first. They had to be solid layers of rock before we could fracture and move along that fault. Okay, same thing on the right. So on the right, a fracture cuts across layers of volcanic ash, so the fault is younger. Okay, the crack that goes through the middle and has displaced them is the youngest feature there. Okay, just like if you broke your finger, right? That break did not exist before you had whatever accident caused it, right? You had your solid finger there, it was a good finger, and then it was broken. Okay, the break came after your finger was already established, existing, and fine. Okay. Our next one is the principle of inclusions. Okay, this is where rocks include pieces of older rocks. So in these images on the left, we have pieces of gray rock that had to be formed and on the surface to be incorporated into the overlying tan unit. Okay, on the right, a red unit contains pieces of a gray unit. The red unit is younger than the gray one. So what that means is you have to have the rock, in this case on the left, we have to have this gray rock already existing. At the surface, you've got little bits and pieces that have broken apart, and then the environment changes. You have a layer of sand put down over those rocks, incorporating them into the new rock. Okay, so a younger unit of rock can contain pieces of an older rock unit. Our next rule sounds similar, and it kind of is. This is the principle of intrusions. So the previous one was inclusions, what was included in the rock. This one is intrusions, what is intruding into the rock. So here we're looking at contact effects with something that's really hot. So a younger magma can bake older rock units. So in the image here on the left, a magma invaded the light gray rock and solidified into the dark gray rock. The magma caused effects along the contact by heating or baking the light gray rock. So along the edge of that magma chamber, we're going to be able to see a bake zone. So that magma had to intrude into a pre-existing rock because it baked the edges that it touched. On the right, a magma, now dark rock, baked and reddened an older rock along the boundary. The magma is younger. All right. So that is the principle of intrusions. So we've got 4 different types of maps here, all looking at the same area in different ways. So what you need to do on your notes here is label what the different types of maps are, and then summarize how the different types of maps depict the Earth's surface. So the first one we're going to look at. So they're all looking at this SP crater, which is in northern Arizona, that erupted about 1,000 years ago, and it still has this beautiful dark lava flow, and it shows up on very clearly on a couple of these images. So the first one is the shaded relief map. Okay, the shaded relief map as far as how it depicts the Earth's surface, so what you would write in the little box on the right. The shaded relief map shows the shape of the land. The shaded relief map shows the shape of the land. And it does that by simulating light and shadows on the hills and valleys. Okay, so you pick a point or a direction that you want this false light to come in from, and that gives you this shaded effect, these highs and lows. So shaded relief map is great to see the shape of the land. Our next one is the topographic map with elevation contours. The topographic map with elevation contours. And if you are any sort of outdoorsy person, learning how to use a topographic map is going to be so helpful as far as hiking or finding a camping spot, or even just plotting out a course to drive. Topographic maps are fantastic. So what they do, what they depict about the Earth's surface is the elevation above sea level and the land surface using contour lines. A topographic map shows the elevation above sea level of the land surface using contour lines. So a contour line is just a line that connects every point that's a certain elevation. So one line will wrap around a mountain, and that all represents 500 feet above sea level. And then you'll see another one closer to the peak, and that circles around the peak, and that's closer to 600 feet above sea level. Okay, so each line represents a certain elevation, a certain height above sea level. Our next is our satellite image. Satellite image uses different wavelengths to show the distribution of different types of plants, rocks, and other features. Satellite image uses different wavelengths to show the distribution of different types of plants, rocks, and other features. So you can tell by the color here, this is not just a photograph. It's not like an aerial photo. This is looking at signals that the surface is giving off. Okay, so recognizing what type of heat signature different types of rocks or different type of plants are giving off. You can plot out all sorts of different things. So this is our satellite image. Again, it uses different wavelengths to show the distribution of different types of plants, rocks, and other features. That brings us to our last one, and the most important one for geologists. That's the geologic map. And that depicts the distribution of rock units and geologic features. The distribution of rock units and geologic features. Okay, that also includes the ages of the rocks, which can be really important when you're trying to figure out what the geologic history of an area is. Right, so again we've got shaded relief, topographic, satellite image, and geologic map. Okay, so all of these images of the subsurface are going to help us infer the sequence of events that formed this area. So if we just use the principle of superposition, looking at these, to figure out the relative ages, we can see, all right, well, the bottom layer, this light gray crosshatch layer, had to be there first, and then this reddish, pebbly conglomerate layer had to come next, and then this darker gray brick patterned limestone came after that, and then this peachy colored speckled sandstone is at the surface, so that happened last. So our oldest layer is on the bottom, our youngest layer is on. So trying to see how that works, to depict the series of events here, the first thing that happens, so in this image we've already got our lower layer, that light gray crosshatch layer, which is probably something like a magma, like a cooled granite, and then it's got this pebbly layer on top of it, and now we're in the shallow sea. So this shallow sea is depositing the gray layer that has the brick pattern. This is a limestone. So this is what you're going to find offshore with all of our bits of coral and shells and things like that. Then the environment changes. So let's say the ocean goes out, it recedes, and now we have a beach where we used to have shallow sea. So on that beach we're going to get a thick layer of sand deposited. So that's why this middle one is sand deposition. And then the last one is erosion. So now that this has been exposed to the surface, depositing sand, now we're going to get a river running through that's going to start eroding or cutting down through those layers. So erosion begins to carve a canyon. And such evolutionary diagrams can be maps, cross-sections, or block diagrams. Okay, we can see this evolution in different forms.